Okay, hopefully everyone will now be able to hear and see me. Okay, yes, let's get this show on the road. Indeed. Thank you, Edwin, and thank you, audience members, for turning up to listen to my talk. My name is Chris Riseley. I'm a research fellow at the University of Bologna in Italy. Before that, I was based in Australia at CSIRO Space and Astronomy. I'm a postdoc, and with 20% of my time, I hold the role of MWA Principal Scientist. And I'm going to be talking to you today about my research using the SKA Pathfinders and Precursors. I'm going to be casting a wide net and going into as much detail as I have the time for. So the structure of this talk, as well as seeing many hopefully pretty pictures, I'm going to tell you all about the contents of a galaxy cluster, the types of non-thermal phenomena that we see in clusters, and particle acceleration mechanisms. I'm going to talk a bit about mini halos, and honestly, the Meerkat meets LOFAR mini halo census that I'm currently performing is going to be taking up the brunt of the time in this talk. Later, I'm going to be talking about some relics, halos, and high mass clusters, touching very briefly on some deep studies of spectacular merging clusters. So without further ado, let's get into the background and tell you what you need to know. So when we talk about clusters and radio astronomy, we're really talking about magnetic fields, which are everywhere in the universe, as we see in galactic magnetized foreground, nearby galaxies, radio galaxies, and in the amplitude of the galactic RM structure, because anywhere we see diffuse synchrotron emission, we are seeing relativistic electrons in the presence of magnetic fields, which generates the synchrotron emission. So magnetic fields are everywhere. And on the very largest scales, in a recent paper that I worked on, led by Tessa Wernström, we did a statistical detection of magnetic fields in intercluster filaments using stacking to detect polarized emission from these accretion shocks. So a little bit about galaxy clusters. These structures form at the nodes and intersections of the universe's large-scale structure, which you're seeing here in some simulations from Millennium. The dominant fraction of the mass budget is composed of dark matter, which occupies about 80% of the total budget, and you generally trace that by lensing and things like the SZ effect. Galaxies themselves, even though they are in the hundreds to thousands in typical clusters, maybe thousands in your more high mass clusters, they only occupy a few percent of the total mass budget. The intracluster medium, which you're seeing here in blue, this is your sparse and your hot plasma. And in this talk, you will see it referred to frequently as the thermal component. This occupies about 15% of the total mass budget. And finally, the final key ingredient we have is the diffuse synchrotron emission. This is your relativistic electrons and magnetic fields, which I will refer to frequently in this talk as non-thermal components. And you are seeing that overlaid here in red. And now that you see the red and the blue and all of these components together, if you're familiar with clusters, you know this is Abel 2744. This is using some data recently presented by my colleague Kailash Rajpurohit, although it's been studied by many other authors in the past. And the key components of what you see in a galaxy cluster, there are many ingredients. You've got your radio galaxies, you've got your radio halo here in the center, and you've got your radio relics. Two are quite clearly visible, although according to the studies that have been published in the past, Abel 2744 hosts up to 4 radio relics. Just 2 of them are much harder to see in this map. And so realistically, when we're talking about clusters, we are talking about rich environments which show rich physics. So let's get into these sources a little bit. Showing another image of Abel 3266 from my paper last year. This is where I want to explain a little bit about why we need the multi-wavelength approach. You see all of these different components that are colorized according to different wavelengths of data. So where you're seeing structures that are yellow, this is your more recent ongoing emission, ongoing injection from things like radio galaxies and propagating shocks, whereas orange through red colors trace increasingly steep spectra. And this is the emphasis of my work, really, because a single frequency doesn't tell the whole story, because putting it in a kind of cartoony representation here and noting caveats about different inhomogeneities, projection effects, radiative losses, inhomogeneous processes, blah, blah, blah. Synchrotron emission is synchrotron emission. So it has this distinct power law behavior, and then at higher frequencies, you have this exponential break. But this is why we need to adopt this multi-wavelength approach, because a single frequency does not tell the whole story. So to get to the underlying physics, we're really talking about understanding the energetics. To get to the energetics, we need to look at the spectrum. And because we need to look at the spectrum and map it in as much detail as possible, we need to take this multi-wavelength approach. And this is the essence of my research program, which I referred to in the title of this talk, CLASP, because we use this multi-wavelength approach to get to the underlying physics. And really, we're trying to answer the question of what powers diffuse radio emission on the largest scales. Now I've talked about relics, and I've talked about halos, and I've talked about radio galaxies, but let's dive a bit into the non-thermal zoo of phenomena in galaxy clusters. I'm not principally going to be talking about radio galaxies. I'm going to be talking about phenomena associated with the intracluster medium itself. We have more or less three pseudo-distinct classes of source dating back of the order of 2 decades to this paper in Kempner et al. 2004, which is one of the first efforts that I'm aware of to really classify and clarify between the different types of sources. You have your classical radio relics and your classical radio halos, and there's sort of the order of 100 or more of each that are known at the moment. These are your megaparsec scale radio sources. And on smaller scales, you have the much less well explored, much more enigmatic radio mini halos, and there's only of the order of 40 of these detected to date. And you can see the kind of different spatial scales we're talking about here. Relics and halos are very much megaparsec scale sources, whereas mini halos are much, much smaller. They are typically, canonically, only sort of 1 to 300 kiloparsecs in size. In terms of the physical mechanisms that power these sources, it's quite commonly accepted that radio halos are powered by some form of MHD turbulence injected into the intracluster medium following merger events. And radio relics are powered by some form of merger shock. The most commonly accepted mechanism is some flavor of diffusive shock acceleration, or DSA, although some of the latest studies are showing that DSA does not tell the whole story. There are some caveats to DSA that are being explored in various systems, both observationally and numerically. Mini halos, it's a little bit more complicated, and the jury is still out. The classical debate has been between turbulence or hadronic processes, and I will mention those in more detail later. But some of the most recent work that my colleagues and myself have been heavily involved in is actually revealing that perhaps some form of hybrid scenario is responsible for the generation of mini halos. And part 1 of this talk is very much going to be devoted to the topic of mini halos. And part 2 of this talk, which will only be a couple of slides, will very much deal with your larger scale emission, your radio halos and your radio relics. So getting into mini halos, part 1 of this talk. Mini halos are what have really been exciting me in the last few years with the instrumentation that has now been made available to us observers. Mini halos are canonically small-scale diffuse radio sources associated with the intracluster medium of relaxed cool core clusters. One of the canonical examples is the mini halo hosted in the Perseus cluster. And so you see here, you can see all the various galaxies in the cluster. The source extends for about 300 kiloparsec. And you can see this diffuse emission that follows the thermal plasma of the intracluster medium. In terms of energy input, the 2 different scenarios that have been proposed in the past, you have hadronics, or secondary cosmic ray electrons, or turbulence, which is generally in the form of mini halos, believed to be induced by core sloshing. So when we talk about hadronics, we talk about generation of secondary electrons through the inelastic collision of cosmic ray protons and thermal protons, which generate various flavors of pion that then decay into these relativistic cosmic rays, gamma rays, and a variety of neutrinos. This is very much a non-exhaustive list. How do we get these relativistic protons in clusters? Well, the answer is in the case of cool core clusters, relaxed clusters, is injection by active galactic nuclei. These massive particle accelerators that accelerate protons and other particles up to relativistic energies. And so these sources pump out these cosmic ray protons, which then collide with the thermal plasma of the cluster and generate these relativistic electrons. Conversely, turbulence is generally believed to arise from core sloshing, and this was detected and reported in Perseus in this paper by Sanders et al. In 2020. So you can kind of see the sloshing motion going around and around in the cluster in the X-ray surface brightness here. A more down-to-earth way to visualize this is looking at the sloshing of wine in a wine glass. If you see your sommelier sloshing the wine around, this is kind of the motion that we're talking about in clusters. And so in the mapping presented by Sanders et al., you can actually see distinctively these classic sloshing spirals. Sloshing should lead to cold fronts, which are seen in several clusters hosting mini halos. And there's a variety of different predictions and mechanisms that we can use observationally to try and distinguish between these scenarios. But the balance between these mechanisms is still an open question, because at some level, secondary electrons will be generated in clusters because AGN are ubiquitous, and cosmic ray protons have a longer lifetime in the ICM, so they can diffuse out and fill a lot of the volume and then collide with the thermal protons of the intracluster medium. As a result of the various different processes, one of the key tools we like to use is the radio spectral index, because turbulence is an inherently intermittent process, both on spatial scales and temporal scales. And so we expected to see many more inhomogeneities in the spectrum. Whereas in the secondary model, we are generally expected to see a typically more homogeneous spectrum. But this is one of the key questions. One of the textbook examples of a mini halo that has been studied a number of times in the past is this cluster RxJ1720. In some old narrowband data from the GMRT, it was revealed to have this sort of central structure with a wing off to the left. Now, in some newer LOFAR data presented by Nadia Biava, who's a former student here in Bologna and is now a postdoc in Germany, Nadia used LOFAR low frequencies to study this self-same cluster, and you see the main components here in the center and this radio galaxy up here, but then there's all of this emission that is very much not seen at higher frequencies, and so we immediately know that something is different. The spectral properties are very different in the different regions. You have your typical spectral index of -1 in the center. It steepens towards the east, and then this ultra steep component towards the southwest is extremely steep with a spectral index of around -3. One of the other tools in our toolbox is the radio to X-ray correlation, and you're going to see a few of these plots during my talk. So one of the things that we like to do is we like to study this correlation between the radio and X-ray surface brightness. The strength tells us how well the thermal and non-thermal components are connected. The slope of the correlation provides insights into the acceleration mechanism and the distribution of thermal and non-thermal particles, because as you go to fainter X-ray surface brightness, we're typically looking at regions towards the cluster outskirts. The structure tells us exactly about whether we have different regions with different mechanisms, and then the spectral dependence, i.e. if there's any change in the correlation slope for the same region with frequency. All of these different insights together give us views into the acceleration mechanism going on. And so one of the things that Nadia found in RxJ1720 is these different components show remarkably different correlations. But one of the unresolved questions is whether this is actually genuinely different physical processes going on in those regions, or are we talking about different microclimates? So delving into the Meerkat meets LOFAR mini halo sensors, this is how we answer this question. We take a statistical sample of mini halos and we study them with exquisite multi-wavelength broadband data uniformly selected. So between Meerkat and LOFAR, which as you well know, are on opposite sides of the world, we take LOFAR, probably the most powerful low frequency telescope at the moment, and we combine that with Meerkat, probably the most powerful mid frequency telescope at the moment. And then we use these data sets together, combined with archival VLA and GMRT data, plus uniformly selected Chandra and XMM data. We use these data sets, we synergize them, and we get these insights into the radio spectrum. And I'm just throwing this cartoon here again, just to remind you of why we're doing this. We want to explore the full radio spectrum insofar as we can. So the spectrum tells us about the underlying emission mechanism. The variation in observed properties with frequency tells us the magnetic field and cosmic ray distribution and acceleration mechanism. And then finally, the insights from Chandra and XMM provide us insights into that thermal and non-thermal connection. Now, as I mentioned, these clusters are on opposite sides of the world. So the intersection of the observable sky for each of them, where we can still get long track observations and get good sensitivity, gives us a sample of 13 mini halos. So this is what we did. We got 74 hours of priority A Meerkat time in the Open Time 2020 call. We're making use of LOFAR surveys and other data sets to provide the low frequency view. And I've got 3 different clusters to present to you from the Meerkat meets LOFAR census today. And I'm going to give you a little bit of a then versus now. So then, with these previous data sets, these are older narrowband data sets from the GMRT, VLA, and likewise GMRT, all overlaid on optical observations. And you can see the sort of mini halos are relatively small. We're talking, a very few 100 kiloparsecs. But then with the new data we have on MS 1455.0, which I'll just refer to as MS 1455, Abell 1413, and finally Abell 2142. All of these are spectacular examples from the census. These first 2 have been published last year and earlier this year. And then Abell 2142 is the latest cluster to be written up by myself, and the paper is getting into a good advanced draft state. Coincidentally, these clusters kind of form a sliding scale between relaxed, non-merging systems, because MS 1455 is very much relaxed, to disturbed clusters, because Abell 2142 is a merging system that is known to host some cold fronts. So it's kind of potentially a remnant cool core scenario that's been disrupted but not completely disrupted by a merger event. And Abell 1413 is somewhere in between. It straddles the line between relaxed and disturbed in various ways. The new insights we gained from MS 1455. Let's take a look at the non-thermal view for starters. In all of these comparison panels, where you'll be seeing 2 panels, I'll be showing Meerkat at 1.3 gigahertz on the left and LOFAR at 145 megahertz on the right-hand side. So from our Meerkat data, which is extremely sensitive, even though we are firmly in the northern sky here, we're at declination of plus 22, Meerkat sensitivity is still phenomenal. We recovered diffuse radio emission up to about 600 kiloparsecs in size, which is twice the size that it was previously believed to be, this mini halo. The spectrum, which you're seeing here on the right, is not ultra steep. We have a spectral index of around -1, whereas previous studies of mini halos always said that the spectral index was very steep, typically -1.3, -1.5 or steeper. But perhaps that is related to the quality of previous data sets. And as you can see from the overall orange to slightly pinky tinged color here, the spectrum is rather homogeneous across the mini halo. We looked at profiles along different directions towards the north and towards the southwest of this mini halo, and we see clear evidence of multiple components, because you can't fit a single exponential profile here. Well, you probably can to the north wedge, because the surface brightness drops off precipitously, but certainly along this southern direction, we see clear evidence of a second component emerging. And the interesting thing is, when you look at the thermal view of MS 1455, we see this kind of inverted 6 or flip 6 structure, which I refer to in these talks. We have this inverted 6 structure, which is an absolutely key piece of evidence for a large-scale sloshing spiral. One of the things we found in this study was that we have clear core sloshing in MS 1455. In fact, the known cold fronts in this cluster, which are not yellow here, and they are in fact cyan, they are not separate. They are not separate parts of the cluster, but actually they are tracing edges of the sloshing spiral in the intracluster medium. If you think about the wine in the wine glass that is the potential well of MS 1455, you can imagine the core sloshing. And when you overlay the radio emission, you see this this northern cold front, this northern edge, is coincident with where we have this very precipitous drop in the radio surface brightness. And the southern cold front is where we have the clear evidence that this second component emerging, which is really curious. Because the majority of the bright radio emission is within this cold front, which is where we expect, within the sloshing spiral, which is where we expect the acceleration to be taking place. But how do we get the acceleration on the larger scales? That's still a complicated question to answer. On even larger scales, we see the emission kind of bleeding out further. But one of the key components is this sloshing spiral is a clear sign that we have turbulence, but the homogeneity of the spectral index is less immediately compatible with the turbulence scenario. So it's an interesting case study. Moving on to Abel 1413, again, going into the non-thermal view first. Again, we have Meerkat on the left, LOFAR on the right, and Meerkat's phenomenal sensitivity allows us to recover diffuse emission up to around 580 kiloparsec, which is twice as large as previously reported. And it is also asymmetric. It's very much extended in the north-south direction, but east-west, it's much more compact. The spectral index is, again, not ultra steep and largely homogeneous, but we have tentative evidence of steepening. And really, unfortunately, it's the quality of the LOFAR data covering this region that is prohibiting us from investigating this further. Likewise, the profiles show evidence of multiple components. Fitting was difficult, so I'm not showing any of the fits here. But along both different directions, we do see tentative evidence of multiple components emerging at both frequencies. In the thermal regime, however, there's no cool core in Abel 1413. Here we're comparing MS 1455 and Abel 1413, and you can tell immediately from the color scale, the central temperature is much higher in Abel 1413 than MS 1455. And likewise, there is no sloshing spiral. However, this doesn't mean there's no turbulence. This means we're dealing with a slightly disturbed system, and so perhaps the turbulence contribution is greater. This is a warm core. We're talking about an asymmetric mini halo with an asymmetric surface brightness distribution. The galaxy distribution is elongated in the north-south direction. So these are all clues that we are seeing a system that is undergoing turbulence. Let's jump into the point-to-point correlation for these two systems before going on to talk about the third one, because it's interesting to compare and contrast. I just want to quickly remind you that the strength of the correlation we're interested in because it tells us about the strength of the connection. The slope tells us about the particle acceleration mechanism and the distribution of thermal and non-thermal components. The structure tells us about perhaps having different mechanisms in different areas. And the frequency dependence, well, is that expected for mini halos? This is something that is a completely unknown field, realistically, until this census came along. But having a steeper slope at higher frequencies would mean that the radio falls off. Well, having a superlinear slope means that the radio falls off faster than the X-ray. X-ray surface brightness is a proxy for the radius. So if we see a steeper slope at higher frequencies compared to lower frequencies, this means we see spectral steepening, which is totally expected in the turbulence scenario. But the same slope at different frequencies is more indicative of the hadronic mechanism. And so these are the point-to-point correlations for MS 1455 on top and Abel 1413 on the bottom. Always Meerkat on the left, LOFAR on the right. And don't strain yourselves too much to read the numbers. You can go and look at them in the papers. But for both clusters, we're seeing a superlinear slope, which means that the non-thermal distribution is more peaked than the thermal distribution. MS 1455, the numbers are the same at both frequencies. It's frequency independent, which means that we don't see a spectral steepening. And curiously, we see the same behavior inside and outside the sloshing spiral, which means that even if we're seeing slightly different turbulence properties, then the properties of the acceleration appears to be subject to the same mechanism. Whereas in Abel 1413, we see a very clearly frequency-dependent slope. The slope is steeper at higher frequencies than lower frequencies. They're both superlinear, but it's steeper at higher frequencies. So this means in Abel 1413, we're seeing spectral steepening, which is totally expected in the turbulence scenario. And so the key takeaway from looking at these two clusters is we're trying to do away with talking about turbulence versus hadronics and which scenario fits better on balance. But we're moving into a regime where we're starting to explore both turbulence and hadronics being responsible for the generation of mini halos. We're talking about a hybrid scenario with perhaps different mechanisms dominant on different scales. And this is a really interesting and promising avenue for investigation. And we kind of looked into that mathematically, a very small amount with Abel 1413, but it very much bears further detailed investigation and numerical work. Briefly, I also, as a brief aside, these studies have also shown that there's a wide field bonanza to be had with these clusters, because even just zooming out a little bit on each of these clusters and showing a region around a megaparsec away, we start to see that with Meerkat's phenomenal sensitivity, we can do amazing wide field science. And it's not just in these maps, but we also see bent-tailed radio galaxies galore. This one is around half a degree away from MS 1455. We see on average around one giant radio galaxy per Meerkat field. And we see some of these odd radio circles or AUKs, which are very much all the rage these days. There are quite a number of papers being published on them. Unfortunately for me, this one here is a known AUK. It's AUK4. It sits about 40 arc minutes away from Abel 2142. But with Meerkat's phenomenal sensitivity and field of view and resolution, we're able to do some cool science with it. So now let's dive into Abel 2142. This is a spectacular cluster. It's high mass, and we see many tailed radio galaxies, these spectacular tailed T1 and T2, and these other groups that are around the periphery. Even at high resolution of around 10 arc seconds, we see two components in the halo. We see the core and we see the radio ridge. The key points are, though, that once we take these data, we subtract as many of the interfering sources as we can, because as you can see, there are many, many point sources in all of these fields with Meerkat's phenomenal sensitivity. Meerkat recovers emission on scales up to around 1.5 megaparsec. So we're seeing the main two components of the halo here, plus we're seeing other components emerge. And just as a brief note, this dot-dashed silver circle denotes a radius of 1 megaparsec centered on the cluster center. Now, when we pull LOFAR into the picture and overlay the LOFAR contours, we're seeing essentially the inner roughly 2 megaparsecs of Abel 2142 just chock full of synchrotron emission. And instantly we know from comparing these Meerkat and LOFAR maps by eye is that the spectrum is going to be steep, because Meerkat, despite its phenomenal sensitivity, does not recover the diffuse emission in the cluster outskirts yet. I think we would need to go a lot deeper, and that's some numbers that I'd like to run for perhaps a future ultra deep Meerkat field on this cluster, because it's extremely rich. Overall, the spectrum is steeper than we were dealing with before, but it's not ultra steep throughout the regions where Meerkat recovers diffuse radio emission. And I will note that this is the first cluster in my sample where Meerkat does not see more emission than LOFAR sees. That is testament to Meerkat sensitivity and to the steep spectrum emission in this cluster. And in Abel 2142, some of the key insights from the thermal point of view, I don't have nice maps to show you, unfortunately, but Abel 2142 is an interesting case because it's a merging cluster that shows at least 4 different sets of cold fronts, which perhaps indicates that these cold fronts are the remnants of a cool core that was disrupted during a merger event, not a massive cataclysmic merger like you see in some clusters, but a merger that was significant enough to disrupt the cool core and set off extreme core sloshing. And so we're seeing these cold fronts throughout the cluster. One of the really interesting things that I'm doing at the moment with Able 2142 is looking at radial profiles, because they've been quite powerful in the other clusters. But changing things up a bit and looking at the profiles along the three major arcs, it's obviously very hard to do towards the northwest because we have these intervening radio galaxies, and I would not be confident in the results even if I had subtracted those sources. So I will not be exploring those regions. Looking at these, what we're doing is we are fitting the canonical model of the e-folding exponential model, which you can read about in various papers, trying to fit one or two components to each of these directions. Towards the southeast, where we know we have two components, the inner component, the secondary component, and then this larger scale emission. In fact, we only really see one large scale component at low resolution. We're talking 60 arc second, 1 arc minute here. Towards the southwest, instead, with Meerkat, we only really see one principal component, but with LOFAR, we see a second component emerging on larger radii. And then finally, towards the northeast, where Meerkat and LOFAR both detect extended emission on larger scales, we see clear evidence of two different components. And so the emerging picture from this is that a low resolution along the southwest arc following the main radio ridge, at low resolution, we only see one component with e-folding radius of around 220, 240 kiloparsec. The story is different when we go to higher resolution, and we study this at 30 arc second resolution. We then start to see two components emerge, but the signal to noise is lower because it's a more complicated situation to study. Towards the southwest, we are starting to see two components emerging, and likewise, the second component emerges also for Meerkat at higher resolution. And towards the northeast, we have a clear confirmation of two components. The e-folding radii are very similar, although not as much for the second component e-folding radius. For LOFAR, it's much larger because LOFAR recovers emission on much larger scales. This is an extremely rich system, and this is very much ongoing work, so stay tuned. Studying the point-to-point correlation is also extremely insightful in Able 2142. Here are the plots. At high frequency with Meerkat, we see a superlinear slope, but at low frequency with LOFAR, we see a sublinear slope, which, to the best of my knowledge, is very much unique in studies of these kind of systems. But this is something I need to dig into further. This is ongoing work. And this is not just a byproduct of the fact that the spectrum is very steep in these outer regions. Using a common set of regions and repeating the fit, we see a slope that is closer to linear at low frequencies, but using only the regions where both Meerkat and LOFAR detect emission, i.e. where the surface brightness is high enough and the spectrum flat enough to detect, we still see a sublinear slope with LOFAR and a superlinear slope with Meerkat. As for the physical interpretation of this, well, the spectrum is getting, the slope of the correlation is getting steeper as we go to higher frequencies, which means we have spectral steepening. But aside from that, this is something where we need to put our brains together and run some simulations and figure out exactly what this means. So as I said before on my previous slide, Able 2142 is a really rich, complicated, and interesting system to study. So stay tuned. This is evolving. Okay. Part 2 of my talk. This is going to be much quicker, so don't worry. Talking about radio relics, halos, and high mass clusters. I just want to show a couple of really cool examples from previous and upcoming work. Spectacular systems. I can hardly talk about spectacular merging systems without referring to Abel 3266, which I published a paper on last year and did a whole press release. This is a complicated merging cluster with two primary subclusters, one of which can be decomposed into two subclusters, and at least 5 subgroups in the cluster periphery. This is a complicated ongoing system, as evidenced by the something like 8 resolved tailed radio galaxies hosted by the cluster. It also hosts a radio relic. And now most relics have power law spectra that hold over a very broad frequency range, such as the well-studied toothbrush relic. But the wrong way relic in Abell 3266 hosts this very sharp broken power law spectrum, which completely poses a very strong challenge to all of our understanding of DSA and requires us to go back to the drawing board a little bit. It also hosts this highly extended radio halo that we only see after applying some clever spatial filtering algorithms to the field, and that's what you're seeing here in white. It hosts this wrong way relic, multi-component radio halo, 8 resolved radio galaxies, this ultra steep spectrum fossil up here towards the northwest that at high frequencies, i.e. above the break, has a spectral index approaching -8, which is the highest high frequency spectrum that I am aware of, and many, many more. So if you're interested in rich clusters, feel free to go away and have a read of the paper we published last year. There's some follow-up work coming out with other ASCAP observations, and we've recently been awarded a significant amount of time to do wide field VLBI on all of the radio galaxies in this cluster to understand exactly the merger dynamics, for example, with these various tailed radio galaxies, bent tails showing clear interactions with the cluster and allowing us to probe cluster weather. And likewise, I could also hardly talk about spectacular systems without mentioning Abell 3667. I wrote my first author paper on this cluster, but the question of whether this cluster hosts a radio halo was recently settled in a paper last year by Francesco de Gasperin using Meerkat data. This cluster is confirmed to host a radio halo. However, I'm in the process of carrying out a joint study with MWA, ASCAP, Meerkat, and EROZeta, and you're seeing the low frequency MWA data at 154 megahertz here in the red color and contours, and we detect the radio halo and the bridge region between the relic and the cluster center, but we also detect the full downstream emission from this spectacular northwest radio relic, which is something that even with Meerkat's phenomenal sensitivity, the spectrum is too steep to recover here, given the present data products. So stay tuned for this upcoming study. It's a really fascinating system, and I'm personally very pleased to get back to studying this cluster. So wrapping up to give people time for questions. Clusters are highly enigmatic objects. I'm drawing big picture conclusions here. We're performing the Meerkat Meets LOFAR mini halo census. I'm studying individual clusters in rich detail using multi-wavelength data. Even those relaxed clusters have having a lot going on. These are highly dynamic environments that we can use to study a wide range of physical processes. I hope I've made it clear just how essentially the multi-messenger or multi-wavelength approach is, using radio, X-ray, optical, and SZ to really piece together the full picture of what's going on in these clusters. We've learned a lot about particle acceleration mechanisms, the thermal, non-thermal connection and magnetic fields in clusters, galaxy evolution in dynamic environments. But the new insights gained from these works are bringing new questions and new challenges to our understanding of core sloshing in mini halos, particle acceleration in radio relics, how we generate these wrong way relics, how do we generate relics with these kind of broken power law spectra, how do we generate multiple component halos and mini halos. All of these challenges require advances in our understanding. If you want to read any more about any of these clusters that I've mentioned, then feel free to take a look at any of these papers. And at this point, I will stop, say thanks for listening, and take questions.
Okay, thank you very much again, Chris, for the talk. Very interesting indeed. So I think we can start with questions from the participants. Otherwise, maybe I can start with a question. So you're using LOFAR to recover some of the large scale emission that is not observed in Meerkat, but you're using HBA observations. So I wonder how much could you recover using LBA? Or that would be useful or no? Or what do you think?
So that's a great question. It depends really which system you're talking about. So in the case of Abel 2142, in this paper by Luca Bruno et al., I mistakenly wrote Luca's first name there. Apologies, Luca, if you're watching this. So there's a recent paper by Bruno et al. Who published LOFAR, HBA, and LBA data on this cluster. It's highly worth a read. It's really interesting. Now, the LBA is very good. The LBA data can be made very good. It's challenging because of these low frequencies, a combination of instrumental and physical effects add up to make LBA data challenging to work with. Particularly in a lot of these clusters, we're talking clusters that are at very low elevation for LOFAR. All of the ones that I've published so far, MS1455, Abel 1413, and Abel 2142 that I'm working on, are not at the ideal declination in the sky for LOFAR observations, because LOFAR, like the MWA, is an aperture array. And so once you go further away from zenith, you lose a lot of your sensitivity. The data becomes more challenging to work with. And so on the whole, it's just extremely difficult. And in the case of MS1455 and Abel 1413, we do have LOFAR LBA data in hand, and those data are being processed. But we're talking about systems also that are much smaller on the sky. And so realistically, what we gain, we gain a fair amount in terms of sensitivity, but we lose a lot in terms of resolution. And so going deeper with the HBA would be my preferred option for exploring MS1455 and Abel 1413 better in more detail.
Okay.
That's a very long answer. Sorry about that.
Yeah, no problem. Okay, so I have another question. I got a question from Keegan. So my question is, when you do the analysis in which you split the diffuse into different sectors like a pizza, so how do you think this is a good idea to do, for example, with another kind of sources, for example, as a radio galaxy that has loss of extended emission, so you can learn more about the source and about the emission mechanisms? So that is my question, and maybe Keegan can tell us what is his question as well.
Just to give Chris a little bit of time for the first question. Chris, do you want to answer the first question before I ask mine?
Yes, absolutely. So when it comes to sources like radio galaxies, absolutely 100%. It's all very well to look at, so taking a step back, with all of these kinds of sources, it's always important to look at the integrated properties because that tells us a lot. But the integrated picture doesn't tell the whole story. If you just look at the integrated fluxes or integrated spectra, then you can lose information on fluctuations or regions that may have different spectra which indicate different processes. So in terms of dividing radio galaxies into different regions, I agree 100% that it is an excellent avenue for investigation. It gets a bit difficult when you're looking at radio galaxies because the structure can be, particularly in clusters, as you can see here in Abel 3266, the structure can be a lot more complicated. So you've got to be careful with designing your sectors. But one of the other avenues of investigation, there's a technique that I believe was developed principally for VLBI activities, but has been adapted and adopted by the sort of arcsecond and lower resolution radio community to look at profiling along ridge lines of radio galaxies. There are a couple of automated tools, and the name escapes me right now, but if you search it using your favorite search engine, then you'll be able to find them. There are some really interesting tools to use to look at defining radio ridgelines along complicated radio galaxies in an automated or semi-automated manner. And so I think that the application of those tools to few arc-second resolution radio data would be extremely insightful, yes.
Okay, so Keegan, your question?
Hi, thank you very much, Chris, for the talk. Wonderful talk. To bridge the gap between the MeerKATs and LOFAR data, do you plan to use MeerKAT UHF data?
Ooh, yes. So MeerKAT UHF band is very, very promising. Now, many of the same challenges that I've mentioned for LOFAR working at low elevations also equally apply to MeerKAT UHF band at these kind of declinations, because most of these targets are also not at optimal elevations and declinations for MeerKAT. So the challenges of imaging at lower frequencies are exacerbated at observing these kind of targets. So UHF band would be extremely interesting. It would also be particularly a worthwhile comparison to make, to compare and contrast MeerKAT's UHF band with things like UGMRT data at these kind of elevations, these kind of declinations, rather, I should say.
Right. Right. Just to say that, like, the census is very difficult because it's not optimal declinations for either LOFAR or MeerKAT. So
exactly. When it comes to other targets, though, other targets that would be at much more optimal declinations for MeerKAT observations, those kind of intermediate frequency ranges between your meter wavelengths and your centimeter wavelengths, very, very much insightful, because you kind of get into a sweet spot, as I've shown with some of these ASCAP studies as well, which occupies a similar frequency range to MeerKAT UHF and L-band, sort of in between. That frequency range is very insightful because you get into that long wavelength regime, but you're still retaining good, meaningful resolutions. So yeah, for targets that are much more optimal declinations, MeerKAT UHF band, L-band, S-band, fill in the spectra, get the whole story, get the underlying physics.
Great. Looking forward to chatting more. See you soon.
Absolutely. Yeah. See you soon in Bologna.
Okay. Thanks.